So the stuff we go over today will hopefully seem familiar to you because we're going to do exactly the same things with position versus time and velocity versus time graphs that you learned how to do in Science 10. Okay? There is absolutely nothing new with those two graphs in this course. Okay? So hopefully it all seems familiar. The big thing here, guys, with graphs, with all types of graphs, but these ones in particular, is this. We don't want you to memorize how to get stuff from a particular graph. Okay? Because I know that happens a lot in Science 10. I teach Science 10 and people just memorize, oh, well, displacement's the area under the line, and this is how I get acceleration, and they just memorize it. That's fine when you only have two graphs to remember. Okay? But when you get to Physics 30 and you've got between 30 and 40 different graphs that you are going to have to use, it's going to get pretty confusing to memorize every last thing that you can get from each of those 30 to 40 graphs. Okay? So what we want you to focus on, and what I'm going to demonstrate, is how to analyze a graph. Okay? Then you only have to remember one thing, how to analyze a graph, and you can apply that to every graph you encounter. Okay? And that'll be much more useful than memorizing how to get something from each kind of graph. Okay? Which again, probably even in Physics 20, could probably get you by. I just don't want you to start relying on that because then someone's going to kick that crutch out from under you next year. Okay? And I don't want to see you fall down. So we're going to learn how to analyze each one instead. All right, so we've got our key points for today. We've got to understand what information can be read from the two kinds of graphs that we're going to go over. And again, that's part of the analysis that we're going to go over. And understand that graphs and equations from kinematics show the same information in different ways. What we're going to end up seeing here is that a lot of the formulas you're familiar with, V equals d over t, acceleration is final velocity minus initial velocity over time, those kind of graphs, or those kind of formulas, sorry, are actually derived from a linear function on a graph. They actually come from that. Okay, so that's what we're going to be looking at a bit here today. Okay, and lastly, learn that kinematics equations, like I say, are derived. So, oops, I already went over that one. Okay. A position versus time graph shows me two things. And this is not a trick question. What are they?
Position and time.
Position and time. Right? It tells me, or I can read directly from this graph, where the object is at various points in time. The shape of the graph can also tell me some things. It can tell me about the nature of the movement that object is undergoing. Those movements, or the nature of those movements, is something that can be applied to any graph. It doesn't have to be a position versus time graph. If I'm looking at any graph, doesn't matter what's on the x and what's on the y, if the graph looks like this, what is happening?
It's standing still.
Yeah, if it's a position time graph, you're right. It's totally standing still in that situation. But no matter what kind of graph this is, it's telling me that whatever's on the y-axis is the same. It's not changing. So on a velocity time graph, that would mean that it's traveling at a constant velocity. On a position versus time graph, it means it's staying at a constant position. If it's stock values over time, it means that your stock is worth the same amount it was when you bought it. Right? Those kinds of things. Does everyone kind of follow what I mean? That's the kind of analysis we want to be able to do, rather than memorizing. When a graph looks like this, it means this. Well, then you got to memorize that for every graph, and that's hard. Okay? If we can analyze that from every graph, that's going to be easier for us. Okay? And we talked a bit about this yesterday, but if I have a graph that looks like that, what is it telling me?
The y value is decreasing.
The y value is decreasing. So whatever is on the y value is going down, but it's going down at a constant rate. Okay? Because it could be going down at a non-linear rate. This is a linear rate. Okay? This would have a slope, and it would, we'd be able to calculate the rate at which it's going down. I could also have something like this, where it's going down like this, not like that. That's a new y-axis. Is that still showing the y value decreasing? Yeah, but it's decreasing in an inversely exponential way. Okay? That means it started out going down really, really quickly, okay? But now that the number is getting bigger and bigger and bigger, or the the x value is getting bigger and bigger, the amount it's going down is getting kind of smaller and smaller. Okay, still decreasing, but the amount it's decreasing by is getting smaller every time. With me there? If I had a graph that looked like this, and we talked about this yesterday, that's something that's increasing exponentially. Okay, it's going up by a different amount every single interval of the x. Right? So that's the kind of analysis we want to be able to do. And then we can apply that to a particular type of graph. Okay? If this is a position versus time graph, and I see this exponential increase or change in position, I know that each time interval, so let's say our time intervals look like this, okay? Each time interval, the amount the position changes by is different. Okay? It's not going up at a constant rate. Right? Now, if I look further into that and I say, all right, it's not, the position is increasing at a non-linear rate, that means that it has to be going not at a constant velocity, which would be linear. Its position would change by the same amount every time. This object must be accelerating. Because it goes further the next second than it went the second before. The only way you go further in an equal amount of time is to be going faster. Okay? So that's analyzing the graph versus memorizing that a curve on a position time graph means it's accelerating. Okay? I can analyze it, and that can be applied to any kind of graph. Okay? If that was a velocity versus time graph, it would mean that the velocity was increasing at a nonlinear rate. Okay? Something like that. If this was a stock value graph, buy that. Okay? Because it's going up exponentially. Okay? If you buy it on a Tuesday, by Friday, it'll be worth 9 times as much. I'm okay with that. That's the kind of stock I want part of. Okay? So being able to analyze it versus memorize it is a big tool. Okay? So in this graph here, in this position versus time graph, we've got, it's a train, I think. So at the beginning of this graph, we have a straight line, it's diagonal. Right? So in this part of the graph, the object's traveling at a constant velocity because its position is changing by the same amount every second. It's traveling at 180 kilometers per hour. So this is one of those European bullet trains. Or like the one apparently they're going to put in between Calgary and Edmonton. Apparently now that's in the works. A bullet train between Calgary and Edmonton. I don't know. Would anyone else take that? I don't know. Like I think about that and I'm like, that'd be cool. But when I get there, how do I get around? I got to Uber around? I don't have a car now. But I got there in like 20 minutes as opposed to 3 hours. Because we all know that's how we describe how far away Edmonton is, right? Tell people how long it takes to get there. All right, this part here, we can see that the graph is curved, but the curve is getting flatter. Okay, so if the curve is getting flatter, and this is showing me how much position I cover, that means that in this first second, I changed my position by this much, okay? But in this second bit, I only changed it by this much, okay? So you can see that this line and this line are different and that the amount of distance I'm covering is going down. That means I am decelerating or slowing down, okay? In physics, we try not to use the term decelerate because acceleration actually means any change in velocity, positive or negative, okay? All right. Here, they indicate that the object is stopped at the station. Well, I know it's stopped because the line is right. The y value isn't changing, and what's on the y-axis is position, which means it's not going anywhere. Okay? It's stationary. And then here, we've got that exponential increase again. So over this first 0.1 hours, it only goes this far. But over the next 0.1 hours, it goes that far. And then the next 0.1 hours, it goes that far. Okay? The only way it can be doing that is by it going faster and faster. Okay. All right. Would I ask you on a quiz or a test to do what we just did there, analyze the graph?
Yes.
Yeah, absolutely. That doesn't require you to actually calculate anything. That just requires you to look at the graph and interpret it and tell me, what is the graph showing? Okay? That is probably the most important skill you can have when it comes to graphing. More important than calculating stuff from a graph is being able to look at a graph and go, that's what it says.
So it starts off in the negative. How
Mhm.
does that work if it's distance?
Okay, so if it's position, what we're saying is basically that the station is our reference point, and we probably started south of it or west of it. And then when we got there after that, we're actually going the same direction the whole time, right? Our position just happened to be before the station, and then it was after the station. Does that make sense?
Yeah, so it'd be kind of like displacement almost, or not?
Absolutely. If I wanted to, I could calculate the displacement here because I know my initial position, let's just say we start here, okay, is negative 24 kilometers, right? By the time I get to the station, I've displaced myself positive 24 kilometers because I would say displacement is final position minus initial position. My final position is the station minus negative 24. So my position, my displacement will be positive 24 kilometers, right? I was definitely moving forward. I just happened to be in a negative direction to start. Okay? If this object was moving in a negative direction, what would the line look like? Because right now we're seeing that it's definitely moving in a positive or forwards direction.
Like that way?
Yeah. That's an object that's moving in a negative direction for a couple of reasons. First off, I can see that the position is becoming more and more negative. Even though it's still positive the whole time, it's becoming more negative. And secondly, if I calculate the slope of that line, would it be a negative number? Then it's definitely going in a negative direction. Okay? These are all little simple analytical things that we have to be able to do when we see a graph. Okay. All right, quick review of slope calculations here. Okay, I know that sometimes in math you get taught that slope equals rise over run. And while that's 100% true, it is also only good for calculating slope, right? In physics, we like to have tools that have more than one use. Physics is the multi-tool of the toolbox, okay? Why have wrench and pliers when you can have them on the same tool, okay? So, we use this. Y equals m times x plus b. We use the linear function for a graph. Okay, so just quick review here. Y is any y value along that line that is actually on that line. X is the corresponding x value for that point. So if I was selecting this point right here on the line, this would be y. That's weird. And this would be x. Okay, everyone with me so far? All right. What's this one called?
Y-intercept?
It's the y-intercept. What part of the equation represents the y-intercept?
B.
B. Okay. B is the value of y when x is 0. Okay. And then m is the slope. Okay. So, yes, slope equals rise over run. And I can prove it with this equation. If I manipulate this for m, I'm going to have y minus b over x. Well, I'm pretty sure that if I take this number and subtract this number, that's the rise. Yes? Right, because that would show me that right there. Well, that's the rise of the line. That's how much it goes up, okay? And since this is x, and x starts out at 0, is x, the value of x, the run? That's how far it goes over. Okay? So we use y equals mx plus b because we can calculate any part of that equation with that equation. Whereas with rise over run, it's not as easy. Okay? It's a little bit easier to do this with y equals mx plus b. So we're going to use that a lot, including in our lab on Monday. All right, is that ringing a bell for everybody? All right, so we got this graph right here. It's a position versus time graph. I would like you to write down on your paper right now, in what two parts of the graph is the object, or sorry, not necessarily two, in what parts of the graph is the object moving forwards? And it's not two. And in what lettered parts of the graph is the object moving forwards? Just write it down on your paper for now. How many people had A, E, and F? Good. Right. We know that in those parts of the graph, the object is moving forwards because its position is becoming more positive. It goes from 0 to 6. It goes from -10 to -4, and it goes from -4 to 0. Okay? It's definitely moving forwards in those three parts of the graph. Where is the object going faster? E or F? Okay, why E? You're right, why E?
Because it's like a shorter, it's hard to explain, but it's like the slope is, I don't know how to say it.
Steeper.
Yeah, steeper.
Yeah, that's the steepest slope. Okay, now that requires us a little bit of memorization that the slope on this graph represents velocity. Okay, but we can justify that here right away. Okay, if I have this formula here, m equals y minus b over x, the one we just looked at a minute ago, on this graph, y would be my final position. B would be my initial position because it's where the object was when x was 0 and x is time. Right? And then x is time. Well, I'm pretty sure that's how we calculate velocity, right? Okay? That's another analytical tool for graphing. I don't have to memorize that the slope of a position-time graph is velocity. I can prove it. Okay? All I have to do is write out the slope formula and then plug in what's on the y-axis and what's on the x-axis, and I'll be able to figure it out. Okay? A similar thing happens on a velocity versus time graph. If I have a velocity versus time graph, so now I've got meters per second here, and I've got seconds here, and I've got a line that looks like this, okay? When I calculate the slope of that line, it's still y minus b over x, but now y and b aren't positions, they're velocities. Y would be my final velocity. B would be my initial velocity because it would be how fast the object is going at time 0. And x is still time. What does that calculate? Anyone remember from Science 10?
Acceleration.
Yeah, that calculates acceleration. Okay? We can analyze a graph as opposed to memorize. All right. Okay, I would like you to calculate a couple of things for me using this graph. See what we remember from Science 10. This one will take you less than 10 seconds. What's the total displacement of this object?
0.
0. How do we know that?
Because the initial position and the final position are the same.
Right, the initial position and the final position are the same. If we recall, we know displacement equals final position minus initial position. My initial position is 0. My final position, also 0. Okay, so while this object went a bunch of places, it ended up back where it started. All right, this one will take you a little bit longer. Calculate the total distance traveled by this object. Okay, and you're probably going to have to do this piece by piece. All right, so distance is scalar. Right? It doesn't care which direction we go, it just cares how far do we go. So in order to figure out how far we go in total, we have to figure out how far we go in each part of the graph, and then do what with those numbers? Just add them up. Right? So in this first part, in part A, we go from a position of 0 to a position of positive 6. So we go 6 meters there. How far do we go in part B? Nowhere, right? It stays at a position of 6 and it's stationary. Then we go from a position of positive 6 to negative 10. So how far do we go there? 16 meters. All right, and then we go from negative 10 back to 0 over 2 sections. I can simplify my work here by going, I can combine these two, okay? And that's going to be another 10 meters. So 10 plus 16 is 26, plus 6 is 32 meters. All right, everybody follow what we did there? Okay. We still had to kind of do that final position minus initial position thing for each section of the graph, and then we just said direction doesn't matter and added them all together like we would for any other scalar quantity. All right. 2 more things I want you to calculate. One will take you no time at all, and the other will take you about 15 to 20 seconds, because you've already done most of the work. Assuming this trip takes 18 seconds, what is the average velocity and average speed over the whole trip? Okay, what's the average velocity? 0. Right. We already calculated that the displacement was 0, and velocity is displacement over time, so velocity is 0. Okay, now to calculate speed. Oh, just hold off. I'll get the answer from you in a second. Or did you have a question?
No, I have an answer.
Okay.
Is it 1.8 meters per second?
Oh, yes, it is. Okay, so 1.8 meters per second. How do we get that? Well, we know that speed is total distance divided by total time. We already did all the work for that. We know it was 32 meters. And I told you that this whole thing takes 18 seconds. It's 32 over 18. Okay. Everyone all right with that? That is totally the kind of thing I would ask you to do on a quiz with a position versus time graph. Okay? I could ask you to calculate velocity, distance, displacement, and speed. All right, is that ringing a bell? Feeling a little bit familiar from Science 10? Okay, because I know I asked my Science 10 classes to do exactly that, okay, on their unit exam and their final exam. Okay, no, we don't need that. All right, when we were talking earlier about what the shape of graphs can mean, okay, we've got a position versus time graph here, and it's all curves. Okay, so what is this object doing basically the entire time?
Going.
Moving. Yeah.
It's accelerating.
Yeah, there's different rates of acceleration, but it's certainly accelerating the entire time. There's no parts that are showing a linear change in position. They're all showing exponential changes in position, okay, which means that the object is accelerating either positively or negatively, okay, throughout this movement. Where is the object speeding up? Part A, definitely. Anywhere else?
From B to C.
Part of the way from B to C, yes. Not the whole way, but part of the way, right? Anytime the line gets steeper, whether that's up or down, then we know that the rate at which the position is changing is going up. Even if it's going up in a negative direction, it's still getting bigger. Okay? Anywhere where the line's getting flatter, that means the rate at which the position is changing is getting smaller. Yeah, slower. Right? We're slowing down because we're not changing our position by as much. Right? So in part A, we're going faster and faster until we get to about here. Because now the line stops getting steeper and starts getting flatter. Okay? And then right after the cusp of that little parabola, okay, it gets steeper, but now in a downward direction. And then, for a very short period of time, okay, it does that. And then, what is this line doing? Is it getting flatter? Okay, so that object is slowing down then, right? Okay. What is this a graph of?
Could it be like a car speeding up and then just stopping, turning around, and then going faster in a different direction maybe?
Yeah, it could be, but for a car, there's one part of this graph that wouldn't really work. But it could be. What you've described is what's happening in this graph, for sure. It's true. I would never ask you a question. It's totally unfair for me to ask this question on a test or something like that, seeing if anyone could kind of figure it out.
Learn something new, a ball.
Yeah, anything thrown up in the air. Okay? This part of the graph here would be when I'm accelerating the object in my hand, making it go faster and faster. As soon as it leaves my hand, what starts to pull on it?
Gravity.
Right. Okay? And gravity slows it down, slows it down, slows it down. For an instant, it's stopped. And then it falls back down. And the reason that the two halves of this parabola are mirror images of each other is because in both parts, it's accelerating at 9.81 meters per second squared. It's just in one part it's moving upwards, and the other part it's moving downwards, but the acceleration is the same in both parts, so that's why they look the same. Okay? And then the last part of the graph would be me catching it and bringing it to a stop. Okay? Again, totally unfair for me to ask you, here's a graph, what's happening? Yeah, describe it, totally. You guys described it perfectly. Okay? But to say what is actually happening, I mean, that's taking a wild stab. Like it's hardly fair to say that. Okay? But I could totally and fairly ask you to describe what's happening in this graph, if not identify what's happening in this graph.
If you asked us that question, described it, and we said, oh, it's like a ball being thrown in the air, would that be a valid answer?
I would say it's probably valid, but it wouldn't be what I was looking for. I would be looking for more of a description in the first part of the graph, it's accelerating positively, and then over the parabola, it's accelerating in the same direction, but not moving in the same direction, and then in the last part, it's coming to a stop. Okay. So we got a position versus time graph here. It's got a linear function. Let's see what you remember from using y equals mx plus b here. I would like you to, using the equation for the line, okay, which is right here, okay, when Google Sheets spits these out, which is what I did here, okay, it spits it out like this. It writes it like this, but what it really means is y equals 3.85 times x plus b. Okay, so this is M, X, and B. All right? I would like you guys to see if you can do the two calculations that are requested there. Okay, so for question number 1, they want to know the position of the object after 1 minute. What part of the equation are they wanting me to calculate?
We're trying to find y.
Right.
Because we have x.
Right, we have X, we're given a time, and they say find the position. Position is on the Y-axis, so we're looking for a Y value. So all we have to do is punch in 60 seconds for X.
Oh,
Okay, because we punch in 1, remember the units per time on the Y-axis, or on the X-axis are seconds, but the question says 1 minute. It's a dirty trick, okay? But we have to be mindful of things like that. All right, so we're going to have Y equals 3.85 times 60 plus negative 0.801. All right, so we should get 230 meters, roughly. Okay, everybody all right with that? Okay, so in question number 2, they're asking how long it will take. Am I looking for a Y value or an X value? X, yeah, because time is on the X value, on the X-axis, sorry. Okay, so I've got to manipulate Y equals mx plus b for X, so I'll subtract b and then divide by m. Right, so X will equal Y minus b over m, so that'll be 150 meters, that's our final position, minus negative 0.801, okay, and then we would divide that by 3.85. Okay, so 150 plus 0.801, because subtracting a negative is like adding, and then divide that by 3.85. Okay. So it would take 39.2 seconds. Okay. Is that ringing a bell? And you definitely would have been asked to do stuff like that in Science 10 for sure. All right, here's another thing that I totally do this all the time, especially on unit exams. And it's a 1-mark question. What's the speed of the object, or what's the velocity of the object in this graph? This requires no calculation.
3.85?
3.85 meters per second, yep. Okay, remember, the slope of this graph represents velocity because when I calculate slope and I go y minus b over x, what I'm really doing is taking final position, subtracting initial position, and dividing by time. Okay, so if I ask you what's the velocity of this object, it's right there in front of you and requires no calculation and would be a 1-mark question. You would be surprised how often I see 5 marks worth of work, all of it wrong unfortunately, for that question. Okay, because people think, oh man, that must be a really tricky thing. It is really tricky, but it's mathematically very simple. All right. So I got a position versus time graph here that has 2 different objects on it. Which object is faster, blue or red? Red, how do we know?
It's got a bigger or steeper slope.
Steeper slope, yeah, exactly. Okay. Which one is going to travel further?
That depends.
On this graph. So within the time frame of this graph.
Red will go further.
Red will go further because red is going
Faster.
faster. Okay, doesn't matter where it starts, where like for either, yeah, they obviously start in different positions, but because red is going faster and they're going to travel for the same amount of time, the faster one is going to go further. Okay, so sometimes I give you, like, that could be a multiple choice question, right? That's still showing simple analysis of a graph Okay, it doesn't require you to calculate anything. It just shows me that you can interpret what's going on. Okay, let's take a quick break here. Let's say about 3 minutes within the classroom here, and then we'll start talking about velocity versus time graphs. Oh, during that 3 minutes, this app is the app you're going to need for our lab on Monday. It's free, okay? But you'll need it because it communicates with our little data cards. Okay, just sends all the data to your phone via Bluetooth. You don't have to like measure anything. It's totally awesome. Okay, so if you can have that on your phone for Monday, that would be great. Okay, guys, let's come back to this. Actually, before we get to velocity versus time graphs, let's do a little bit of kind of practice stuff here with the position versus time graphs. Okay, so this is a lot like what you're going to be expected to do on your lab report, in the analysis part of your lab report on Monday for our lab. Okay, you're going to have several data sets, and you're going to have to do basically this type of analysis. So for question number 1, they're asking what's the velocity of each cart. Okay, so that's pretty straightforward because we don't really have to do much for that. Okay, calculate the position of each cart after 12 seconds. Okay, their equations are right in here. And how long will it take each cart to reach a position of 50 meters? Okay, so I'd like you guys to try those right now. I know it's a bit repetitive, but okay, repetition helps trigger the memory. Okay, so we'll do those ones and see how we do that. All right, so for question number 1, okay, what we kind of need to analyze is that obviously the slope of the line on this graph represents the velocity of the cart. So all we have to do is look at the slopes here, and we know that the velocity of cart number 1 is 1.38 meters per second, 2.01 meters per second for cart number 2, and 3.3 meters per second for cart number 3. Okay, 3.39, sorry, meters per second. All right. Now, for question number 2, it's the same calculation, just with different numbers for each cart. Right? We're looking for the position of the cart after 12 seconds. Right? So that's going to mean y equals m times x plus b, just putting in the appropriate numbers for each cart. So for cart number 1, that's going to be 1.38 times 12 plus 0.00952. Okay, that's 9.52 times 10 to the minus 3. So we should get 16.6 meters, and that would be positive, okay, because it's on that side of the graph. All right, for cart number 2, 2.01 times 12 seconds plus negative 0.0524. All right, so we're looking at 24.1 meters as the final position for cart number 2, and for cart number 3, all right, we're looking at 40.7 meters as the final position there. Okay. And then for question number 3, we're solving for x now because we're wanting to know how long. Time is on the x-axis. So for each one of those, x will be y minus b over m, just putting in the appropriate numbers again for each cart. So we would have 50 minus 0.00952 divided by 1.38. So we're looking at 36 seconds for cart number 1. Okay, for cart number 2, we're going to have 50 minus negative 0.0524 divided by 2.01. So that should take 25 seconds. And then for cart number 3, we're going to have 50 minus 0.0381. And then we're going to divide that by 3.39. Now, you'll notice that on each one of those calculations, I did the subtraction operation and then pressed enter before I divided by the slope. If you didn't do that, you probably got pretty much the same number for all of them, okay? And that's because your calculator defaults to do order of operations. So it divided the last number by the slope and then subtracted that from 50. Okay, and that's obviously not what we want to do here. We need to make sure we do the top and then divide the top by the bottom. Okay, so you could put it in brackets and then divide by the bottom or something, but you have to do the top operation first. Okay, so if that happened to anybody, that's why it happened. Okay. All right, questions on that? Like I say, that is exactly what you're going to be asked to do for your analysis on Monday for your lab report. So nothing terribly difficult or nothing you haven't done before. All right, one last thing here before the bell goes, just so we have a graph, a position versus time graph that's not linear. Okay, I would like you guys to try this one, calculating the average velocity of the bus during each of the intervals. Okay, and just so that there's no confusion, this goes to 25 here. Okay, at one hour it's 25 kilometers. This is 33 kilometers, and this is 27 kilometers, I believe. Okay, just because it's kind of hard to read on the graph, because it's kind of small. Right? Okay, let's just look at this one like really quickly here. All right, so obviously for all of these parts, we're not really calculating the slope here because we don't have one single linear function. But what we can do is remember that velocity is always going to be final position minus initial position over time, and we can read those items right off of the graph because it's position versus time graph. So obviously for the first one, the initial position is 0, final is 25, and that takes 1 hour, so 25 kilometers per hour. Okay. For the second part, we go from 25 to 33, so our change in position is going to be positive 8 meters. Okay, and that's going to take, or 8 kilometers, sorry, and that's going to take 1¼ hours, so divide that by 1.25, and we should get our positive 6.4 kilometers per hour. And then for the last one, we go from 33 to 27, so that's going to be -6. That also happens over 1¼ hours. Okay, and so we should get -4.8 kilometers per hour for that. All right. So tomorrow we will go over velocity versus time graphs, and then on Monday we'll do our lab. Okay? And I'll get your quizzes back to you tomorrow.